Welcome to Codex. Our speaker today is Jakob Lemvig, who is an associate professor and head of studies of mathematics and technology at the Technical University of Denmark. Dr. Lemvig is an expert in applied harmonic analysis, signal and image processing, and frame theory. Today, he will tell us about the Gabor frame set problem. Take it away, Jakob.
Thanks, and thanks for inviting me to give a talk here. So it's 7 o'clock in Denmark, and my kids are being put to bed upstairs. So if you hear noises, that's the reason why, and that's also the reason why I don't usually join so often. It's just about in the middle of the bedtime stories. But thanks for inviting me. So I'll talk about the Gabor frame set problem for Hermite functions. So this is joint work with two students of mine, Andreas Horst and Erlang Wiedebeck. And I have here listed 3 papers that I will mention today. So the starting point is the paper by Gröschnik on the mystery of Gabor frames. So he listed a number of puzzles, or at least conjectures on what's called the frame set problems, and one of them were for the Hermite functions. So I will in a minute explain exactly what those conjectures are about. So I worked on that a few years ago, so in 2017, and then I've been it's work with Andreas and Alan that we did a few years ago, and we revived it recently. We never ended up submitting it. So Andreas is now a PhD student with me. So we decided that it was a good time to revive this project, and it's a preprint called on the non-frame property of Gabor systems with Hermite generators. So the outline of the talk is first an overview of the problem. Then I will only speak about what's called rationally oversampled Gabor systems. So, and in particular, I will show some sec transform symmetries. So all our counterexamples are based on these, and I will show how you can. I think to tackle these problems, you need to use some kind of computer software. So I will use some numerical results from Python and show how you can gain insight into the problems from these results, and show in particular how you then prove obstructions to the frame property. And hopefully, so we will post the code soon on GitHub, and also I did some work on B-splines, which is a bit more involved, at least numerically. And I will also, once I have ported the code from MATLAB to Python, I will also post them on GitHub. So my hope is that this will serve as an invitation to some student that will take this code and improve on it, and prove some more things about this mystery of the Gabor frames. And okay, so we will end out today proving that the frame set conjecture for Hermite function is false for all orders larger than or equal to 2. So, and in particular, we will see that the frame set must have rather complicated structure. And so for the Gabor frame, which I called H0, it's known to be true, the frame set conjecture. And I will not share any light on the remaining conjecture, which is for H1. So that conjecture is still open. All right, so the central concepts, it's functions living on the real line. They are in L2, so square integral functions. There are 2 main operators, so that's translation. So you translate a function by an amount k, and then modulation. So that's the frequency shifts. You modulate by this complex exponentials. And here's an example. This is just the second or H2, what I call the second Hermite function. It's a Gaussian multiplied by the Hermite polynomial up to some constant. And once we start translating this, so here it's translated by to the right, and here is modulated by E2, and I plotted the real part of that function. It's of course complex valued. Okay, so these are the 2 operators that we are using. So these are unitary operators on L2 and R. And if you combine these, so you fix what's called a window function G. You fix parameters, so I call them translation parameter A and a modulation parameter B, and then you consider all time frequency shifts along B times M, A times K, where K and M are running over the integers. So this gives you a bi-infinite family of functions, and we call that a Gabor system, and it's called a frame if, furthermore, we can find two constants A and B. So many of you already know this, of course. So A fits as a lower bound and B as an upper bound, and these two inequalities should hold for all functions in L2. And we're interested in this case because this is exactly what gives us unconditionally L2 convergence and stable expansions. Okay, so just a note of terminology, if the upper bound holds, we call it a Bessel system. So there are two classical questions in Gabor analysis that are related with the talk today. So the one is about completeness or totality of a system, and the other one is about the expansion property. So here it's for the Gaussian window, I call it H0. Neumann claimed that the Gabor system spanned by or generated by the function H0 with A and B equal to 1 is total in L2. And Dennis Gabor conjectured that you have a frame expansion of the same system. And right, so here A and B, if you don't remember, these are exactly the translation, the modulation parameter B and the translation parameter A. All right, so but the questions that we here formulate is that we fix always the window G, it's an L2 function, and then we ask for which pairs A and B, and we consider them to be positive real numbers. So they are subset, so they are points in R2 plus. And you can ask the question whether the Gabor system generated by that function is complete in L2, and you can ask the same thing about the frame for frames. And it's the second problem we're interested in today. So that is actually the frame set problem, that is finding f of g. And f of g here is all the set of points A, B, for which the corresponding Gabor system is a frame for L2 on R. All right, so the Hermite functions, they are defined in the following way. It's a Gaussian multiplied by the Hermite polynomials up to some constant. They are eigenfunctions of operators. So the first one is this differential operator H, but more importantly, they are eigenfunctions of the Fourier transform. And the eigenvalues, as you know, are plus minus 1 and plus minus I. And the eigenspaces, I denote those by e to EL, where L is an integer between 0 and 3. Right. So the Gaussian, well, it has eigenvalue 1, as you know, but that in the same eigenspace sits H4, H8, 12, 16, etc. And the other points, they go, well, okay, so when L is equal to 1, we have eigenvalue -1, and there sits the eigenfunctions or the Hermite functions H1 and 5, 9, etc. All right, so what do we know about the frame set for am I able to move it? Yeah, all right, so I'll move it down here. Known results, right? So since these are very nice window functions, these Hermite functions, they're smooth, they have exponential decay, and so they certainly form Bessel systems. And moreover, since they are nice enough, you know that the frame set sits under the hyperbola AB equal to 1. For the Gaussian, it's actually known that the frame set is exactly equal to that set. So every point A and B for which the product of A and B is smaller than 1 is exactly the frame set. And this is the largest possible frame set for nice enough windows. And then for the Hermite functions, you have a certain symmetry property. So if AB belongs to the frame set, then also BA belongs to the frame set, and it's easy to see because the as I just mentioned, the Fourier transform of the Hermite function is some constant times the Hermite function itself. So so therefore, by just taking a Fourier transform of the Gabor system, you end up with a similar Gabor system, but where the role of A and B are switched, since this is how the Fourier transform commutes with modulation and translation. All right, but then you also have the spanning property. So these sets, these Gabor systems for arbitrary A and B, well, I said arbitrary, but I actually mean rational. If they're rational numbers smaller than or equal to 1, then the Gabor system is complete. So this was shown by Böschnik, Jaime, and José Julio Romero in 2016 or 17, I think. Right. Okay, but there are more known results. So you actually know that when A and B, the product of the time sampling and the frequency sampling of your system is small, is sufficiently small, then it is also a frame set. So in particular, it needs to be smaller than 1 divided by n plus 1. This is a result by Böschnik and Lebowski from 2009. And you also know something about the non-frame property. So for all odd functions, you can show that when A and B is p divided by p plus 1, so a fraction of that form, then that pair cannot belong to the frame set. So if we sketch it, we can divide it into 2 groups. So one for even n, so for even order of the Hermite function. And what you know is, okay, we have a symmetry line, and then the green. So this is A, the time parameter, B, that's the modulation parameter. And if a point is marked by green, then that Gabor system will have the frame property. And we know it needs to the frame set needs to stay below this dashed line here, which is AB equal to 1. The yellow area is an area where it's unknown, right? And for the odd n, okay, there's a lot of hyperbolas that we need to look away from. So these are the non-frame property. They're marked by red. And again, the yellow area here is where it's what's unknown. And the conjecture was simple, right? It said, okay, for every pair AB where we don't know, we suspect that it's part of the frame set, so it generates a frame. And so for even n, that would mean that the frame set would be as large as it's possible, and for odd n, it would simply just need to stay away from these hyperbolas listed here. Okay, so this is the frame set conjecture, which we will see is false for all n larger than or equal to 2. So the proof method uses the section form. So the section form is of a function in L2 is defined by okay. So essentially, you cut up the function in intervals of length lambda. You take the sample value for each length lambda apart from each other, or multiples of lambda apart from each other, and then you multiply with complex exponentials, and you make a periodization over this, or you sum up all these. And then, okay, you have the scaling in front of it. That's simply just to make it a unitary mapping from L2 onto to L2 functions of 2 variables on the unit square. So I will usually assume that the generators, so G is sufficiently nice. So here I just listed that G and G hat are part of the Wiener space. So that, for example, guarantees that the section form is a continuous function. So it's a continuous function in X and gamma. So I would like to stress that there are 3 parameters here, right? There's a X, we consider that as a time parameter. There's gamma, that's a frequency parameter. And there's lambda, that's a modulation parameter, or a scaling parameter, if you may. So I use a definition where lambda is outside or there's a parenthesis here. So it's really quasi-periodic on the unit square. So it's one periodic in the gamma direction, and it's quasi one periodic in the x variable. All right. So what that means is that if you know the section form on the unit cube, you know it for any x and any gamma. Oh, sorry, the unit square, you know it for any x and for any gamma. And there's a Poisson summation formula shows that the sec transform can be explained, or can be equal to up to this complex exponential of 1 divided by lambda, right? So if you go from g to g hat, you replace lambda with 1 divided by lambda, and then you switch the role of the two variables as well. So a lot of the proofs uses this formula quite a lot. All right, so that's the sec transform, but there are certain symmetries of the sec transform, and I've listed some of the relations here, and I either assume that g is even or odd function, and I assume that g is either real or purely imaginary function. And in that case, you have the following symmetries. So n is equal to 0 if g is even, and it's equal to 1 if g is odd. So for example, that n that sits here, that depends on whether g is even or odd. And k here depends on whether g is real or imaginary. And from these symmetries, they are immediate to show. You just plug in the definition. You can actually verify some zeros of the sec transform. So if your generator g is even, it has 1 0 at a half, comma a half. And if your generator is odd, it has more zeros, but they sit on a half, comma a half, or 1, comma a half, except for 1/2, comma 1/2. Oh, sorry about that. These are well-known symmetries. So I marked here an area. So what is important for us is that zeros of all right. So that zeros of the sec transform. I hope you can still see my screen here. So this is the case for even functions, and what these results shows us is that if I have a 0, say at located here, so this is a half, comma half, right, and this could be 1/6, comma 1/2. If I have a 0 of the sec transform with that point, I also have a 0 over here, where this is 5 divided by 6. So in general, there's symmetry between zeros according to exactly this axis here. And that's actually also how you can verify. You can verify why you have a 0 sitting at a half, comma half. You restrict the sec transform to the line where your frequency variable is 1/2. So to this line here, and you simply verify that when you restrict the sec transform to this line, then it's odd around the point 1/2. So since it's an odd and continuous function, it must have the 0 exactly at the symmetry point. And you can verify all of the zeros by similar arguments. All right. So how is the sec transform important for us? Well, it characterizes the Gabor frame property for rationally oversampled Gabor systems. So in that case, AB is equal to a fraction, so we call it P over Q. P and Q are co-prime, and then the following assumptions are equivalent: that the Gabor system is a Gabor frame, and that this Cebulski-Cevi matrix is it's a P times Q matrix that consists of sec transform evaluated at a certain number of points. And that matrix needs to have full rank, and it needs to have full rank for all x and gamma on the unit square. So we will actually use just a simple version of this characterization, namely what I call the 0 row failure. So in particular, if you can find a 0 row of the Cebulski-Cevi matrix, then it cannot have full rank. And so we just need to find one x naught, so one value of x and one value of gamma, so gamma naught, for where I have what I call the zero row failure. It's just a row of the Sapolsky-Seebeck matrix that is consists of zeros. Then certainly it has not full rank, and therefore it won't be a frame. So these zeros should be okay. They should happen on a horizontal line, so where gamma is fixed, and in the x variable they should be 1 over q apart, and I should have q zeros, right? So that is it's a short fat matrix, so it has q columns. So I need q zeros. Each of them should be 1 over q apart. So I guess I can go back to my picture here, and right. So in this setup here, if I have let me mark the zeros by blue, right? If I have a 0 at 1 over 6, I have a 0 at 1/2 and a 0 at 5 over 6. Each of these will be 1 over 3 apart, right? They're 1/3 apart. So I have 3 zeros on a where gamma naught is equal to 1/2, and they are 3 zeros separated by 1/4. So in that case, I can then verify that the Gabor system is not a frame. And all our counterexamples will fit this setup by the zero row failure. So the approach we took here is slightly different, right? Because usually you consider lambda as a parameter, and you consider x and gamma as the variables. But here we fix gamma and we fix x, and we consider the section form as a function of the modulation parameter. And the obstructions that we look for, they are occurring on hyperbolas AB equal to 1/2, 1/3, 1/4, and 2/3. That's what we can handle. And the obstructions are now easy, right? Because for even functions, if I can find just one lambda parameter for which the section form is 0, then the Gabor system here is not a frame. So let me try to explain that. Or well, actually, we can look at the second statement here: obstructions for even points. If I can find a lambda for which the section form evaluated at 1/6 and 1/2 is 0, then I know that these two Gabor systems are not frames. So you can go back to the picture I just left, right? Because here in this case, since I have symmetry, it's an even function. So I know I have a 0 already marked by red here. So I have for free a 0 here, 1/2, 1/2. This is simply because it's an even function. And then if I can find just one 0 sitting there, then by symmetry, I have another 0 over here. So I essentially just need to find the 0 here marked with a circle. And that's the entire that's all the obstructions on this slide. It's simply if I can find 1 0 of the Gabor transform, then since I know about symmetries, I have enough zeros of the section form that I know that I have a 0 row failure, and therefore in this case, you see this is the first one here is happening on AB equal to 1/2. This one happens on AB equal to 1/3, and this one happens to AB equal to 2/3. Right. So down here I have a Sapolsky-Seebeck matrix of size 2 by 3, and I have 3 zeros. Oh, sorry. Here the first one is 1 by 3. All 3 are zeros, and over here it's a 2 by 3 Sapolsky-Seebeck matrix, but I have 1 0 row. Of course, the Sapolsky-Seebeck matrix is not 0 for all x and gammas, but I just need to find one value of gamma naught and one value of x naught, and then by continuity, I can of the second form, I know that it cannot be a frame. All right. So if you see in both these statements here, I took gamma naught to be 1/2. I don't have to do that. That could be, but okay, for us, it's enough to consider 1/2. So gamma naught is always 1/2 when I consider even functions, and gamma naught is always 0 when I consider odd functions. In these cases, the section form is actually just a series of this type here. So for the 1/2 case, I have these sign changes, and for the when gamma naught is 0, I simply have functions of this type. It should be a G sitting here on the sum on the right-hand side, of course. All right, so let's try to compute this, right? So I'm looking, so when G is even, I just have to find a lambda for which this function here has a 0, right? So let me go back to the second statement of obstructions for even functions. That's exactly what it says, right? And if I can find a 0, then I know that these two Gabor systems cannot be frames. And so if I have an even function, then every single 0 of this function will correspond to a non-frame property of both these two Gabor systems, simply by this 0-row failure. So let's go to Python. So here I'm using, I hope it's large enough that you can actually see it. So I'm using SymPy. This is symbolic computations in Python, and I have a number of definitions. It's nothing. I define, for example, the Hermite functions, right? So the 5th Hermite function is plotted here. I guess I could, plot any other Hermite function. All right. Okay. Great. So let me. I better run the commands. Okay. I hope this is a danger of doing live coding. So. Right. So here I have the 4th and the 5th Hermite function plotted. But what I wanted to show you was exactly this plot here, right? So x naught here is 1/6, gamma naught is 1/2, and I plot this as a function of s comma lambda. And s here is a number, the square root of 3, right? But lambda here is plotted. These are the values of the section form, and there are certainly a 0 sitting here at 1, and there's another 0 sitting here. And this is for, let me see, these are for the first 4 Gabor Hermite functions. So the blue one is the Gaussian. The green one is the first Hermite function, and etc. The orange one is the H2, and the red one is H3. And so if you wonder which Hermite functions I'm actually plotting the section form of, it's listed here. And if you don't know Python terminology, then the range is like this. So the starting range, the end, and then the increment. So here I plot the first. These are the orders of the functions I just plotted. And down here I plot from range 5 to 8. And increment by 1, right? So this is H5 through H8, and you see there are lots of zeros, right? Every single one of them will correspond to a non-frame property. But there are some similarities that are perhaps not apparent. It is more obvious if I actually plot it as a function. So what I plotted in these two plots are exactly what's written here. So the sec transform as a function of lambda, but now I change lambda into an exponential function. So instead of a lambda, I use kappa, and kappa is just lambda equal to so lambda is equal to 2 times 2 to the kappa. Right, so if lambda is a positive parameter, but kappa is a real parameter, it runs from -infinity to infinity. And if I do the same plot, but for kappa, you will see a plot like this. So here I plotted every second Hermite function, but I could also try to plot the first 4 Hermite functions. And it looks like this. So at least the orange one is even, the red one is odd, and the 2 other functions I cannot say anything clever about. So you can actually show the following, what I call modular characteristics. It depends only on the eigen value of the Fourier transform. So remember EL was the 4 different eigenspaces associated to the Fourier transform. So if L is equal to 0 and 2, I have the following modular characteristics. So what happens here is that the SAC transform evaluated at S, lambda is the same or can be expressed as S divided by lambda. And S here is a parameter, or it's a number whose square is either 2 or 3, right? So it holds in either of these 2 cases. And you have a similar symmetry for L equal to 1 and 3. So you actually see that if we go back to the plots I started out with. So these are plots of this form here, right? So for the blue one, you see that it's symmetric around a lambda equal to 1/2, right? But this part of the curve here can be recovered if you replace lambda with 1 divided by lambda, which gives you the other half of this. And the same thing for the green one. The green one is oddly symmetric around lambda equal to 1/2. Well, if you replace lambda with 1 divided by lambda, you recover the first part of the graph. It's not the case for the red and for the orange one, right? Which is why I really should only plot these for the even orders. If you see for even orders, that's comes here. Okay. All right. Here I have it. It's a little difficult to see, but they are all symmetric around lambda equal to 1. In the sense that if you replace lambda with 1 divided by lambda, you recover the function on the interval from 0 to 1, and also from 1 to infinity. And as I said, that's easier to see the symmetry if you actually go down and look at the symmetry where you replace lambda with some exponential to kappa. And if you do that, then you have symmetries where I again should restrict myself to only the even cases. All right, so here you see the perfect symmetries of these SAC transform with respect to kappa. So what can we say from these modular characteristics? So I call the modular characteristics modular because it's in the modular parameter, and characteristics is a term that comes from theta functions, which has a property of modular characteristics. This is not really as general. These are only evaluated at points, so you could call them point-wise modular characteristics. But when L is equal to 2 and 3, so these are the cases. So L, remember, is again corresponding to the value of the eigenvalue of the Fourier transform. We have odd modular characteristics because there comes a minus in front of it, and the minus here is important. So remember, when L is equal to 2, there's a -1 here, and if L is equal to 3, there's also a minus in front here. So these I call odd modular characteristics. They give the following properties: that the SAC transform evaluated at some points gives you the same with a minus in front, and then the reciprocal of lambda. But if you take lambda to be equal to 1, then you can conclude that the SAC transform needs to have a 0. at this exact point x naught and gamma naught. And this actually explains all the counterexamples that I found in my first paper. This is exactly this odd modular characteristics of this form. And that's enough remember for this obstructions of the frame property, I just needed 1 0 of the section form, and this is what this odd modular characteristic gives me. It gives me a 0 of the section form, exactly the one I need. So that actually already it disproves the frame set conjecture for n equal to 3, 7, etc., and 4, 8, etc. So n of the form 4m plus l, where m is some non-negative integer. And these obstruction points, they are not specific to the Hermite functions. They actually hold for any function sufficiently nice in these two spaces of the eigenspaces of the Fourier transform. So what do we know then in the other cases? So when L is equal to 0 and L is equal to 1. So there we have even modular characteristics. So the minus sign in front of the section form disappeared, right? And from that, I cannot conclude anything. I cannot guarantee these 0 row failures or zeros of the section form. And in fact, I know this cannot be the case because the Gaussian sits in the case where L is equal to 0. And I know that the Gaussian, that this function, this section form cannot have 0, right? Because that would imply that the corresponding Gabor system would not be a frame, and or an associated Gabor system would not be a frame, but that's not the case. The Gaussian has the largest possible frame set, right? Every single point AB less than 1 corresponds to a Gabor system that's a frame. So, but what can we then use this symmetry for? Well, okay, I can double the number of obstruction points, right? If I know 1, I can find 1 more because it's symmetric around lambda equal to 1. But then it also improves the numerical situation, because perhaps you noticed that that something odd happens when kappa becomes small. This is not the true value of the function. This is numerical round-off errors, or it's actually truncation errors of the section form, because I truncate the infinite series. And when lambda becomes very small, I need a lot of terms for this to converge, and this is a problem. So, but since I have symmetry, right, I can just look at the case where lambda is larger than 1, and in that case, I need very few terms for the convergence of the section form. So it's easy to truncate. All right, so let us summarize so far, right? So the frame set conjecture is false for Hermite functions of order I should have not so something. Let me see. Okay. Yeah, that was a typo, but I can get away with half of the cases. So it is when lambda is equal to -1, and when lambda is equal to I can get rid of the cases. So when L is equal to 2 and 3, and the points, so I can find 4 points when n is 2, 6, 10, etc., and I can find 2 more additional points for the odd cases. All right, but from here we need other methods if we want to tackle the remaining cases. So by the remaining cases, you can see 4, 5, etc. Those are the cases missing, and then all multiples of 4 of those 2. However, you can verify the following theorem. So if you have even Hermite functions of order 4 or larger, then you can always find a 0 of the section form. So here gamma is fixed to be 1/2, and x is an arbitrary number between -1/4 and 1/4. So it simply says that there exists a lambda for which this section form is 0. And similar for odd functions, I need to replace 1/2 with a 0, but the statement is the same. And right here, the statement here, you have to be careful because it's not correct for small orders. So how does the proof goes? So this is what is left in the to disprove the conjecture, right? Because I simply apply one of these two obstructions, and for that I just need a 0. But I need to prove zeros, and I want a proof that works for all orders. So for any order n larger than 4 that is even, or any odd n that is larger than 3. So I need a proof that works for all orders, and that took us some time. So it suffices to show that for the even case, that's similar for the odd case, that fix x0 between 0 and a quarter, and you have to look at series of this form, and you have to prove that you have a 0. So first you verify that it's continuous in lambda, and then you show that for large enough lambda it's positive, and then you have to find an interval where lambda gives you a negative value. And the proof relies on a number of properties. So for example, that the first one is that the Hermite polynomials, they have n real and simple zeros in an interval from minus the square root of n 2n plus 2 plus minus that, and then that the roots are convex, which means that the distance between consecutive roots grow as you move away from the origin. And then if you square the roots and if you sum those up, the positive ones, all of them, you will get the following number. So n times n minus 1 divided by 2. And then we needed an estimate of the largest one, so of the largest root, and this lower bound here was good enough. It improves on a bound you can find in the book by Sergio. And then the proof works giving you a 0, and it gives you upper and lower bounds on the 0 only depending on the order of the Hermite polynomial. And the proof relies on the existence of 2 non-negative zeros of the Hermite polynomial, which is why it won't work for the first 3 orders of the Hermite polynomials. Right? It starts working from n equal to 3, and I find the largest 0. There are many more zeros, and we can go back to the plot here. You can see every single 0 here, and in particular when the order increases, the number of 0 grows almost like the order of the Hermite function, right? So if you would plot this for Hermite functions of order n equal to 20, you would get essentially 20 zeros of this section form, and all of those are associated with a obstruction of the frame point. Okay, so that's at least the ingredients of the proof. I don't have time to actually go into the proofs. So the consequences, we're almost at the end, right? That the frame set conjecture there, it's also false for these remaining cases. So n equal to 4, 8, 12, etc., and 5, 9, 13, etc. And you see the symmetry. While in the first cases, the obstruction points in the first paper I did, they were all fixed for all orders. Actually, they were fixed for the entire Fourier eigenspaces. But these obstruction points here, they depend on n, and as n becomes larger, they move away from the symmetry line, so they shoot out because it's the largest 0 that we verify. And all right, so some conclusions from these slides. Well, the frame set conjecture is false, right? And it's false for all orders larger than or equal to 2. It's still open for H1. So for H1 would be the case where you simply verify that only these hyperbolas that are marked here in red are not part of the frame set. That's that conjecture, and we cannot tackle this because H1, of course, it has no positive zeros. So the proof that I just mentioned here, it fails, right? There are not two non-negative zeros. And okay, so, but more importantly, there's no easy description of the frame set of the Hermite functions for these functions, except possibly for, okay, it's easy for n equal to 0, perhaps also for n equal to 1, but certainly not for all the other orders. And one can ask, what are the precise locations? So these new points here, I can only give them up. I can give an upper and lower bound on the point, but not exactly where it's located. So that would be one open problem. Another one would be: are these points isolated points? Are they really just a single point in a area where we have the frame property? I guess not. And one could wonder whether these obstruction points, they are actually part of some hyperbola that lies, I don't know, that goes into the domain in some way, or at least some kind of geometric object, and not isolated points. But yeah, that's. And then how many points are there on these considered hyperbolas? So I only considered 4 different hyperbolas here. So AB equal to 1/2, 1/3, 1/4, and 2/3. And as I mentioned, every single zero here correspond to obstruction to the frame point, and one could wonder how many do you have, right? For a fixed order, say 20, how many zeros would you actually have? And that would correspond to the number of obstruction points. And then finally, you could wonder whether this bound AB equal to less than 1 divided by n plus 1, whether that's optimal. I mean, can you always find an obstruction point that sits exactly on this hyperbola where n is the order of the Hermite function? And okay, so I hope someone else, or at least some bright student, will take it from here. Thanks.
Awesome. Let's thank the speaker by smashing that reaction button. And then questions.